Dear learners, welcome to the course Electromagnetic Fields. In this video, I'll be explaining coordinate systems. In the previous video, we have discussed about rectangular or Cartesian coordinate system. So in this video, I'm going to explain cylindrical coordinate system. Cylindrical coordinate system, the coordinate points are R, phi, Z. The range of variables for the coordinates R is 0 to infinity, phi is 0 to 2 pi and Z is minus infinity to plus infinity. Generally, cylindrical coordinate system is defined by means of three surfaces. The surfaces are R is equal to constant, which is a circular cylinder with the z-axis as its axis. Second surface is phi is equal to constant plane, which is a vertical plane perpendicular to xy plane, making angle phi with respect to xz plane. Third one is z is equal to constant plane, is a plane parallel to xy plane. The point P can be defined as the intersection of three surfaces in cylindrical coordinate system. These three surfaces are illustrated here. The first surface is R is equal to constant, which is a circular cylinder with the z-axis as its axis. The second one is phi is equal to constant plane, which is a vertical plane perpendicular to xy plane, making angle phi with respect to xz plane. Third one is z is equal to constant plane. Is a plane parallel to xy plane. Now, the intersection of these three surfaces define the point P in cylindrical coordinate system. The intersection of any two surfaces out of these three surfaces is either a line or a circle, and intersection of three surfaces defines a point P. The intersection of Z is equal to constant and R is equal to constant is a circle. And also, the intersection of phi is equal to constant and R is equal to constant plane is a line. The point P, which is intersection of all three surfaces, which is represented in this illustration. Here, it is defined as point P. This is point P, intersection of circular cylinder and phi is equal to constant plane and Z is equal to constant plane. Here, the intersection of R is equal to constant and phi is equal to constant is a straight line. This is a straight. And the intersection of R is equal to constant and Z is equal to constant is a circle. This area, this defines the circle. Next, we are going to talk about unit vectors in cylindrical coordinate system. Unit vectors or base vectors. The base vectors, which are similar to Cartesian coordinate system, there are three unit vectors in the R, phi and Z directions represented as AR vector, A phi vector and AZ vector respectively. These unit vectors are mentioned in this figure. These three vectors mutually perpendicular to each other. The AR vector lies in a plane parallel to the xy plane and is perpendicular to the surface of the cylinder. At a given point, it coming radially outward. You note down the AR vector is radially outward from the cylindrical surface. The unit vector A phi vector lies also in a plane parallel to the xy plane, but it is tangential to the cylinder and pointing in a direction of increasing phi at a given point. The unit vector AZ vector is parallel to z-axis and direction towards increasing z. Now the vector of point P can be represented as P vector is equal to PR AR vector plus P phi A phi vector plus PZ AZ vector, where PR, P phi and PZ are the vector components in cylindrical coordinate system. Next we are going to talk about differential elements in cylindrical coordinate system. Consider the point P is r, phi, z in a cylindrical coordinate system. Let us each coordinate is increased by the differential amount. The differential increments in r direction is dr, phi direction is d phi, and in z direction is dz. Now, there are two cylinders of radius r and r plus dr. There are two radial planes at the angles phi and phi plus d phi. And there are two horizontal planes at the heights of z and z plus dz. All these surfaces enclose a small volume which is shown in the figure. The differential length in r direction and z directions are dr and dz respectively. In phi directions, d phi is the change in angle phi, and it is not the differential length. So, due to the change in phi, that is d phi, there exists a differential arc length in phi direction. This differential length due to d phi in phi direction is r d phi. Thus, the differential lengths are dr is differential length in r direction, r d phi is the differential length in phi direction, dz is the differential length in z direction. Hence, the differential vector length in cylindrical coordinate system is dl vector is equal to dr ar vector plus r d phi a phi vector plus dz az vector. The magnitude of the differential length vector is given by modulus of dl vector is equal to square root of dr square plus r d phi square plus dz square. Hence, the differential volume of the differential element formed is given by dv is equal to r dr d phi dz. The differential surface areas in the three directions are shown in this figure. First one is ds vector in r direction. ds vector normal to r direction is r d phi dz ar vector. Next, the ds phi vector is the differential surface normal to phi direction, which is dr dz a phi vector. The third differential surface is normal to z direction, that is ds z vector is equal to dr or d phi az vector. So, the vector representation of this differential surface areas are listed here. Okay, differential surface normal to r direction, normal to phi direction, and normal to z direction are mentioned here. The relationship between Cartesian and cylindrical coordinate system is very important. We should know how to convert the point from Cartesian to cylindrical and vice versa. Okay. Consider a point P whose coordinates are x, y and z, while the cylindrical coordinates are r, phi and z, which is mentioned in this figure. Here the point P is represented in both rectangular and cylindrical coordinates. Now, looking at xy plane, we can write x is equal to r cos phi and y is equal to r sin phi. The z remains same in both the coordinate systems. Hence, transformation from cylindrical to Cartesian can be obtained from the equations x equal to r cos phi, y is equal to r sin phi and z is equal to z. Here this equation, it gives transformation of coordinates from cylindrical to Cartesian. So it can be seen that r can be expressed in terms of x and y as r is equal to square root of x square plus y square and tan phi is equal to y by x. So this the transformation from Cartesian to cylindrical can be obtained from r is equal to square root of x square plus y square, phi is equal to tan inverse y by x and z is equal to z. One important note is while using the equation phi is equal to tan inverse y by x, you should note the signs of x and y. If both are positive, phi is positive in the first quadrant. If x is negative and y is positive, then the point is in the second quadrant. Hence, phi must be within plus 90 degree and plus 180 degree. That means it should be within minus 180 degree and minus 270 degree. Say for example, we consider x equal to minus 2 and y is equal to 1. Here x is negative, y is positive. So therefore phi is equal to tan inverse 1 by minus 2. We have calculated as it is minus 26.56 degree. But the angle should be it should be lying between minus 180 degree and minus 270 degree. So we have to add plus 180 degree with the value. So we will get 154.43 degree. Hence, when x is negative, it is necessary to add 180 degree to phi calculated using tan inverse function in order to obtain accurate values of phi at a particular point. When y is negative and x is positive, then phi is in fourth quadrant, that is within 0 degree and minus 90 degree. That means it may be 270 degree and 360 degree. Similarly, when x is negative and y is also negative, the point is in third quadrant and accordingly phi must be between minus 90 degree to minus 180 degree. That is, it should be lying between plus 180 degree and plus 270 degree. So, 180 degree must be subtracted from the calculated phi value to get accurate phi when both x and y are negative. So, we should give a great attention while calculating phi. We have to make sure the signs of x and y. I hope you could understand cylindrical coordinate system very well. Thank you.